PVM in situ probe-based instruments. PVM is a probe-based vision tool which gives an instantaneous information-rich insight into particle system behavior. And then you can see in the image we have a 400 millimeter long probe which is 19 millimeters in diameter, and the PVM can easily be moved from one vessel to another and is extremely lightweight so that one can use the probe from one vessel and move it quickly to another. On the right-hand side, we see PVM images taken from high-concentrated, opaque, or translucent slurries in real time. And as you can see, we have a probe-based instrument, so no sampling, sample preparation, or dilution is required. And all these images are acquired in real time. The detection of the particles ranges from 2 microns to a millimeter. And we can save a movie sequence as fast as 10 images per second. And this is all done in real time with no sampling. This is an example of some PVM images captured in real time from a crystallization. And what you see in this example is that there's a crystallization which is occurring, and during the cooling of crystallization, there's a phase separation. So this phase separation occurs, and a droplet phase is beginning to form. These droplets were impossible to see by eye, and as you can see in the middle graph, the process was left unchanged, and there was a extensive phase separation. So you can see many droplets formed in this middle image. The important thing here is that these images were captured in real time during live experiment. If samples were taken offline, they were allowed to cool to room temperature and they were filtered very rapidly. However, those droplets disappeared. And you can see the image in the bottom graph at room temperature where the droplets are no longer present. So this is an example where a PVM can be used in real time to really get a true understanding of the particle system and discover information in one experiment that was previously impossible to obtain through months of traditional experimentation. And this is not an exaggeration. In one experiment, we observed this phase separation that was unknown through months of previous experiments. In this next example, we look at a crystallization from a previous users conference presented by Sridhar Desikan of DuPont Pharmaceuticals, now Bristol Myers Squibb. You can see in the top graph at 11:06, we see crystals. And these are images in real time from a crystallization without sampling. In the middle graph, there's a phase separation. And again, what we call oiling out in the crystallization industry, there's a droplet phase formation where there's an immiscible phase. Those droplets can cause problems with downstream processing. Certainly, those droplets can cause impurity concerns or flow property concerns or other downstream processing issues. And as you see, PVM was able to detect the point at which those droplets formed. In the final graph, at 2 o'clock in the afternoon, the droplets are again disappeared, and the crystals began to grow. This was, in fact, an anti-solvent addition crystallization, and the conditions when that droplet phase formed related to the temperature and the solvent ratio. And with the knowledge of the phase separation boundary and conditions as identified by PVM, the process could actually be scaled up and avoid the phase separation during scale-up. And that was proven by DuPont and Bristol Myers Squibb. And it was an integral piece was the PVM. And again, by running one simple experiment, we were able to understand that phase separation and then look at the boundary conditions, why that occurred. In this example, we look at Merck Pharmaceuticals, looking at the use of online monitoring of crystallization of a polymorphic compound using Lasentec, PVM, and Raman. We see a milled seed in the first example, and then crystal formation and crystal growth. So PVM confirmed that there's a growth rather than nucleation, and we see the growth of needles. In the next slide, we see the process continue, and there's a large number of needles in these images. However, as the process went along and progressed, in the bottom image, we see an unexpected form. And this was detected by PVM. And in fact, this was at such a low concentration that it was below the detection limit of Raman. and it was actually below the detection limit of offline microscopy. And if you sampled with offline microscopy, probability was that we would not see that unexpected form, just because that unexpected form was in such low concentrations. However, PVM can image thousands of particles per second. So we're quickly detecting if there is that other form present just by looking at thousands of particles and looking at 10 images per second from the PVM. So for polymorphs, what Merck would actually say here is that for polymorphs exhibiting different morphologies, PVM may be more sensitive than Raman in detecting the presence of different polymorphs at low concentrations, as well as the end of the turnover, or the transition from one polymorph to another. So PVM, again in this example, was used to discover information in one experiment that would have taken weeks or months to discover with traditional experiments. And that was actually proven here by Merck. In this example, we look at a paper from the University College Dublin. It's actually a PhD thesis, where they compared inline PVM images to offline microscopy images. You can see in the left, the top image are PVM in-process images, and in the bottom, the offline microscopy images after filtration, drying, and slide preparation. So they look similar on the left. However, on the right, we see dendritic growth in the top PVM image. So these are dendrites which grow out of the surface roughness of the crystal later on at the endpoint of the crystallization. These could cause problems with washing of those crystals. They could cause problems with filtration or flow properties downstream, or even dissolution properties downstream. The offline microscope image shows none of those dendrites because all those particles are crushed when the slide is prepared with a cover slide. So this is again a reason to use inline microscopy, inline PVM, to really get a true understanding of the agglomeration, the surface roughness, and basically the mechanism for which particles are growing. In this next example, we look at actually an agglomeration occurring. This is a granulation process in a paper that was originally presented by GEA Nairo, where in the image you can see the PVM installed in a fluid bed, and they were controlling the airflow rate and the spray rate to maximize spherical growth while eliminating agglomeration. And you can see in the images below the nice growth of those particles over time. Those are snapshots. That's just an image several points in time as we progressed during the granulation. Precise size control provided the correct dissolution profile for these particles, and agglomeration resulted in undesired dissolution profiles and a loss of yield. Later on, you can see agglomeration actually occurred and PVM detected it. So here in these images, you can see the bridging in these particles, and they're actually getting stuck together. So PVM actually detected the moment and the conditions when agglomeration occurred, and PVM provided visual feedback which allowed the engineers to adjust the spray rate and the airflow rates to avoid further agglomeration. Without PVM, if we waited to get these measurements offline, it would have been too late, and the batch would have not been complete. Or the batch would have been complete, and also we would have a loss of yield. So the value of using PVM is to discover information in one single experiment that was previously impossible through even months of traditional experiments. A common thing that we've heard is that in one day we learned information that would have otherwise taken months to discover. And once that information is obtained, users can use the PVM information to understand the particle system dynamics and allow the system to be optimized quickly while running the fewest experiments possible.